Today I'm going to talk about the theory of special relativity and what led up to it. But first, we need to discuss the classical theory of relativity. This theory dominated physics for at least 300 years, so Newton's time until Einstein. So we have an object here moving at a constant speed, a truck, and it's moving at a speed of 10 meters per second. And we have two people inside the bed of this truck, and they are throwing a baseball from one person to the other at a speed of 2 meters per second. Notice that all of the speeds here are constant, so there are no forces that, and particularly no external forces. So no forces are acting on the truck because it's moving at a constant speed. Remember, F is equal to ma. So forces are zero, acceleration is zero, velocity is constant. We also have a bystander that is observing and measuring the speed of the baseball. And again, the people throwing the baseball are going to perceive the speed of being 2 meters per second, but the bystander, since the bystander is at rest with respect to the truck, is going to observe a speed of 10 plus 2 meters per second, so 12 meters per second, and you add the two speeds together because they're moving in the same direction. So the baseball's moving in the same direction as the truck. If the truck and the baseball are moving in opposite directions, then you subtract the speeds. So that's the classical theory of relativity. So let's see how that works with light. So what we're going to do now is we're going to look at the headlights, and in this truck it will still move at 10 meters per second, but the bystander is going to be in front of the truck and measuring the speed of light coming out of the headlights. And also there will be a passenger observing what's happening and measuring the speed of light also coming from the headlights, making it a passenger, since this is probably not a good idea to do as a driver. So both persons are measuring the speed of light as they observe them. So how would you calculate what these two observed speeds should be? According to classical theory of relativity, and practically all physicists before Einstein, since Newton's time, you should add the two speeds because the light is moving in the same direction as the truck. But, so Einstein said, no, you shouldn't add the two speeds. It's not 3 times 10 to the 8th meters per second plus 10. It is just 3.00 times 10 to the 8th meters per second, the usual speed of light, not the speed of light plus the speed of the truck. So how did Einstein come up with his idea? The crucial experiment was the Michelson-Morley experiment. So in this experiment, you have a laser beam that is being shot at a half-silvered mirror. So the half-silvered mirror reflects half of the light and lets through half of the light. So half goes through, half is reflected. So the half that goes through goes to the right, and the half that's reflected goes up and hits a plane mirror, which reflects the light back to the half-silvered mirror. And again, when it hits the half-silvered mirror, half goes through and half is reflected. So when this happens, some of the light will, from the two different light beams, the one going left to right and the one going up and down, will combine and go to the detector. Now, this light that comes from these two light beams coming together will form an interference pattern. And you can understand the result of this interference pattern by thinking of how the two different orientations, so the left-right orientation versus the up-down orientations, the speeds of light could be different. And if they are different, then will form different interference patterns. When we think of the two light waves combining to form this interference pattern at the half-circular mirror, they form by constructive and destructive interference. Then they tried doing this experiment at different times of the year because the Earth revolves about the sun at different rates depending on the time of year and at different locations, and as well as varying the orientation of the interferometer. And in every case, they determined within the uncertainties of the experiment that the speed of light was a constant. They did two major things to improve the experiment. First, they made the arms larger, the L1 and L2 lengths, and secondly, they made them with more care. That is, they made them more precisely and with more accuracy. This increased the observed versus calculated effects of any possible speed of light change due to orientation. This experiment was improved over a course of almost 50 years, starting with Michelson in 1881 and continuing with Morley. Then in 1930, the last experiment was completed by Juice, and the factor between the calculated versus observed effects of any possible change in the speed of light changed from a factor of 2 to 375. That is, the speed of light was determined to be a constant to a very great degree. To summarize, there were two reasons that caused deep unsettlement and two reasons that advanced Einstein's ideas. The first was that the classical theory of relativity had been around for at least 2 centuries, but it was found to be incorrect. In addition, it makes sense in light of our everyday experiences. Thus, this theory is still used for objects moving much less than the speed of light. To get further information, please see the resources below. The other difficulty is that the mixture of space and time is an outcome of the theory of special relativity. Depending on where you're observing an event, as well as your velocity and position, affects how you measure the time elapsed during the event and length measurements. These odd ideas make it difficult for scientists to think outside their own frame of reference at the time, yet there were 2 events that helped push this theory through and get these scientists to shift their reference frame. The first was the Michelson-Morley and other related experiments, which verified the theory that the speed of light is a constant. The second is Maxwell developed a set of 4 equations that describe the interactions between electricity and magnetism. The unusual part about these equations is that they did not transform as expected according to the laws of classical relativity when you shift from one frame of reference that is stationary to another frame of reference that is moving at constant velocity. If you use the special theory of relativity, then they do transform as expected when shifting to a new frame of reference. However, this was a new theory being published in the 1860s and the special theory of relativity being published in 1905. Thus, scientists were initially unsure what to do. These scientists did have a way of getting around this. First, they posited that the existence of an ether through which the light travels, since they thought all waves have a medium that they travel through. Secondly, they assumed that Maxwell's equations are only true if you're stationary with respect to the ether. So if you're not moving with respect to the ether, then the speed is 3.00 times 10 to the 8th meters per second. However, today, the ether is considered an unnecessary assumption, and the speed of light has been measured with a superb accuracy to be a constant. This makes light, electricity, and magnetism simpler to understand while making it difficult to ascribe objects moving close to the speed of light. However, the special theory of relativity has held since 1905 when it was published. Please utilize the links below in the description if you would like to investigate these ideas further. Thank you for joining me in this exploration of the history of relativity.